heat engines and refrigerator. Case refrigerator. Heat pumps. The second cycle that we were not able to complete was the one indicated that possibility of transferring heat directly from a low temperature body to high temperature body. It is not possible without any work. This can of course be done with a refrigerator or heat pump. This can of course be done with a refrigerator or heat pump. A vapor compression refrigerator cycle, which was introduced in Chapter 1 and shown in the figure 7, is shown in this picture separately as a cycle. The working fluid is working fluid. Is the refrigerant. Such as or ammonia, which goes through a thermodynamic cycle. It goes through thermodynamic cycle. Heat is transferred to the refrigerant in the evaporator. From the refrigerant in the evaporator. It is from the low temperature body and is QL as shown in the picture here. where its pressure and temperature are low. Work is done on the refrigerant in the compressor. On refrigerant. And heat is transferred from it in the condenser. Right. Heat transferred from the refrigerant in the condenser, shown here, QH. Where its pressure and temperature are high. High pressure, temperature is high, P and T high, and P and T is high, T is low for the fluid. The pressure drop as the refrigerant flows the throttle valve. The pressure drop through the throttle. Thus, in refrigerator or heat pump, we have a device that operates in a cycle. We have a device that operates in a cycle. That requires work. And thus transfer heat from a low temperature body to a high temperature body. Heat transfer a low temperature body to high temperature body. The thermoelectric refrigerator, which was discussed in Chapter 1 and shown schematically, is another example of a device that meets our definition of a refrigerator. The work input in the thermoelectric refrigerator is in the form of electrical energy. and heat transfer from the refrigerant space, the cold junction, and from the hot junction to the surrounding area. The efficiency of a refrigerator is expressed as coefficient of performance the efficiency of a refrigerator is expressed in terms of coefficient of performance. Which we design it with the symbol beta and COP. For a refrigerator, the objective that is the energy sold is Q QL. The heat transfers from the refrigerator space refrigerator space, low temperature body, and the next the energy that cost is the work. W. So the coefficient COP or beta equals to coefficient of performance, the energy sold, QL, and on the work, energy cost. Which is QL on QH minus QL. A wholesale refrigerator may have a COP of 2.5 COP, whereas a deep freeze unit will be closer to 1. Lower cold temperature space or higher warm temperature space will result in lower value of COP, as will be seen in the next section. For a heat pump operating over a moderate temperature range, a value of its COP can be about 4, with this value decreasing sharply as the heat pump's operating temperature range is broadening. It should be noted that a refrigeration or heat pump cycle can be used with either of two objectives. It can be used as a refrigerator, in which case the primary objective QL, the heat transfer to the refrigerant from the refrigerated space. It can also be used as a heating system. So refrigerator or heat pump as heating system In this case, QH is energy sought, and W is energy cost. So beta COP is for this case is QH on QH minus QA, and shown with the beta prime. This also follows that for a circle given beta prime minus beta equals to 1. This is not also COP. Beta prime. For a refrigerator cycle, we have this relation beta prime minus beta is 1 because beta prime QH and minus beta is beta prime. Before we state the second law, the concept of thermal reservoir should be introduced. A thermal reservoir, another description, thermal reservoir. A thermal reservoir is a body to which and from which heat can be transferred indefinitely without changing temperature of the reservoir. Is a body to which and from which heat can be transferred indefinitely without changing temperature of the reservoir. Does a thermal reservoir always remain under constant temperature? The ocean and the atmosphere approaches the definition very closely. Ocean, atmosphere, it is useful to designate a high temperature reservoir and low temperature reservoir. Sometimes a reservoir from which heat is transferred is called a source, and the reservoir to which heat is transferred as sink. sink and source. As defined, sink and source observe heat transfer to cycle. Anyway, the next section is the second law of thermodynamics.